Chapter 5, Z-Scores, Location of Scores in Standardized Distributions, Part 4. So in this part of the lecture, we're going to focus on how we can use Z-scores as a way of applying inferential statistics. So again, inferential statistics refers to the process of using sample statistics or sample data to draw conclusions about a population. So up until now, we've been focusing on the use of Z-scores applicable to populations, but the same can be used for samples, and in doing so, we will be able to engage in inferential statistics. So populations are the most common context for computing Z-scores. For example, looking at computing a Z-score of someone's IQ, which will enable us to express that person's IQ in relation to the mean of all IQ scores. So you may sometime in your life hear someone say that you are 3 standard deviation units, which implies that you're very different from the norm, from the average of whatever the characteristic is that you're talking about. So we can apply all that we've learned thus far in relation to population and use it to understand the implications of Z-scores when applied to a sample. So it is possible to compute a Z-score for samples. In fact, I've already presented the equations to do so in a previous lecture. So for a sample, Z is equal to X minus M, right, over S. So again, the structure is the same and the variables represented are the same, but the notation is different because we're using a sample versus a population. And also, if we want to convert a Z-score back into an X value, the equation is X is equal to the mean of the sample plus the product of the Z-score multiplied by the standard deviation. So again, the structure is the same, it's just the notation that's different when we're using Z-scores for a sample. So again, the purpose of a Z-score is to indicate the exact location of a score in relation to the mean. So it indicates relative position of score in a sample, and it indicates the distance from the sample mean. Again, the sign tells us if we're above or below the mean, and the value indicates how many standard deviation units that particular score is from the mean. Now, at this point, we are strictly talking about scores in relation to the mean, but we're going to move towards this idea of samples compared to the population mean when we get into Chapter 7. And the reason for that is because we wouldn't conduct good research using just one data point. We need a collection of data points so that we can draw conclusions about a population. But we're going to learn about that step by step by first looking at scores and then using that information and applying it to converting sample averages into Z-scores. So in a sample distribution can be transformed into Z-scores. And again, the shape of the distribution remains the same, and we have the same mean and standard deviation for M and S. So again, if it were we're converting all X values of a sample into Z-scores, then the mean of the distribution is still 0 and the standard deviation is still equal to 1. So looking ahead to inferential statistics, the interpretation of research results depends on determining if a sample is noticeably different from the population. So again, the treated sample. So we'll have instances where we may be comparing a sample to a population if we're lucky enough to have population parameters available to us, or we may be comparing samples to samples. One sample is representative of the untreated population and one sample is exposed to the treatment, which stems from the manipulation of the independent variable. So once a treatment is administered and we are able to make comparisons, we want to know, is the group that received treatment noticeably different? So we need to define what we mean by noticeably different. So one technique for defining noticeably different is to use Z-scores. And we've seen in our text this idea of, one standard deviation unit above and below. That represents the majority of scores. 70% of scores are going to fall within that region. And again, based on our understanding of frequency, that makes sense. The highest percentage of scores are occurring around the mean, that most scores are similar to the mean in a normal distribution. And we know that we can go out 3 standard deviation units above and below the mean to capture the majority or almost all of the scores. We would capture approximately 99% of all scores 3 standard deviation units out. But we tend to think anything that's beyond a z-score of 2, beyond a z-score of 2 is expressing something that's different from the mean, that it's noticeably different, that it no longer falls in that common region. And we as researchers have to determine, is the difference that we see due to chance, sampling error, or is it due to the fact that the treatment was effective? And we'll learn how to statistically make that determination. But for now, we understand that noticeably different implies 2 or more standard deviation units away from the mean. Again, if something is close to the mean, it means it's similar to the mean. If it deviates from the mean, then it's indicating that it's different from the mean. So here's a visual of what we are going to engage in, or what we can apply when we engage in research. So we usually hypothesize about some original population without treatment. And then we select, and again, this is denoted by M, the population size. And then we take a sample, a smaller subset, preferably representative of the population, is just smaller in size. The proportions and all the characteristics that are demonstrating the population are simply in a smaller ratio than they appear in the larger population. So it's a small mini population per se. So we have our sample. We expose that sample to treatment, and then we analyze that treatment. And one method of research says that then we compare treated sample to untreated population. And we'll learn about this when we engage in a z-score test. And this requires that we have population parameters. So we have to have the information about the population to do this kind of comparison. But here we took a subset of the population and used a sample to expose it to treatment, and then we're going to compare is the end result, and normally it's the mean that we're comparing, the average score of the treated population compares to the population parameter, the mu, the average of the untreated population. And then we decide, is this noticeably different? Are they different? And to determine that, we would calculate a z-score of that sample mean and see if it indeed is beyond 2 standard deviation units from the population mean. And a little precursor to what we'll be studying later is this idea that if we don't have population parameters available, we would take a sample, and that would be the untreated sample. So again, if we don't have population parameters, we can just take a sample that is then deemed as the untreated sample, and then when we take a sample, so notice that we have 2 samples that are being compared to one another. When we treat one sample, then it's a comparison of this group, right, compared to this group. And so again, one sample is serving as a representation of the untreated population, and the other sample receives treatment. And so then we compare the two to see if there's a difference between the 2 groups. So these are different methods by which we can draw comparisons. Again, in most cases, we're not going to have access to population parameters. So in most statistical tests, we will find or use a sample to mimic or serve the place of the population. And then we treat the other sample so that we can draw comparisons to see if the manipulation of the independent variable was effective. So let's put this to work for us. In Chapter 5, there's example 5.11, and it outlines this research of testing a growth hormone on rats. So we have a population of adult rats, and we're told that the average weight of the untreated population of rats is equal to 400 grams. So that's the average weight of a normal rat, lab rat. And we want to determine if a growth hormone has an effect on the weight of these rats. And an additional piece of information that we're given is that the standard deviation is equal to 20 grams. So again, by definition, that says that the majority of adult rats weigh 400 grams, but there's variation in that weight, and on average, these rats deviate from this average of 400 on average by 20 grams. So again, we're understanding that from the center here, right, and if we were to go up 20 grams, that puts us at a score of 420, right? Because we would take one standard deviation unit is equal to 20 points, add it to the mean, and we understand that that's equal to 420. Also on the negative side, or the values below the mean, that places us at a weight of 380 grams. So again, the majority, or 70% of adult rats, are going to weigh between 380 grams all the way to 420 grams. So that's where most of adult rats weigh. So that's the range, the normal range. Again, the majority at 400 grams, but there's some deviation. But within that deviation, we have approximately 70% of rats weighing between 380 and 420 grams. Okay, so next, what these researchers did was take one rat at birth and begin injecting it with this growth hormone. And once it reached adulthood, then that rat was weighed and to determine if the growth hormone was effective. So we administer the growth hormone to one rat, and in the end, their adult weight is 418 grams. And before I go any further, what I want to do is use this as an example of demonstrating what the research and the null hypothesis would be, as well as identifying the independent-dependent variable. So here I've identified what the null hypothesis would state. Again, the notation for the null is H sub 0. The growth hormone has an effect on growth, or we could say weight, right? Growth, that's denoted by weight if we want to be more specific. So the growth is in relation to the weight, because that's what we're measuring in the end. And the research hypothesis states that, and again, the notation is H sub 1, the growth hormone does have an effect on weight. So again, the null always says nothing's happening, does not have an effect. And the research is saying something is happening, it does have an effect. So note the difference between the two. The independent variable is the thing that we're manipulating, so it's the growth hormone. So we're going to administer that to one rat. Normally we'd administer it to a sample, but this is just an illustration of how we convert one X value into a Z-score to determine if this is noticeably different. And the dependent variable is the weight. That's what we're going to measure in the end. So again, here's that same graph illustrating the mean in the center. So again, the mean of the adult rats is 400 grams, and we had a standard deviation equal to 20 grams. And we indicated that we took one rat at birth and administered this growth hormone, and at adulthood, when it reached adulthood, it weighed 418 grams. So we're going to use this value to determine if this is noticeably different, meaning was the independent variable, the growth hormone, effective in significantly increasing weight. So we would convert that to a Z-score. So we take X minus mu and divide by our standard deviation. and our Z is equal to 418 grams minus the average of 400 grams over 20 grams. So our Z-score, okay, in our calculator is 418 minus 400. That's equal to 18. Divide by 20. Our Z-score is equal to 0.9. So in other words, an X value of 418 is 0.9 standard deviation units above the mean. It's a little less than 1 standard deviation unit. Again, I indicated that this area constitutes 70% of adult rats' weight. So it's within that common range. We would consider this to be not very noticeably different, that it's still within that range of being represented by this average weight of 400. So in this case, we wouldn't have enough evidence to say that this growth hormone had a significant effect on weight, that once this growth hormone was administered, the end result was really no different than the average. And the difference that we obtained of 418 grams is just simply due to chance, and that perhaps the genetic makeup of this rat to begin with tended to be a little bit larger than the norm, than the average. In the next scenario, I apologize if there was a bit of a pause there. The next scenario relates to a rat, again, taken at birth and given this growth hormone. And in the end, when that rat reaches adulthood, it weighs 450 grams. So again, these are two different scenarios, and they're just conducting research on one rat at a time, and now they're saying this particular rat now weighs 450 grams. So again, we want to find out, is that noticeably different from the norm? We convert that score into a Z-score. So Z is equal to X minus mu over standard deviation. Z is equal to 450 minus 400 over 20. So in our calculators, 450 minus 400 gives us 50. Divide by 20, and we get a Z-score equal to 2.5. So a weight of 450 grams is 2.5, 2.5 standard deviation units from the mean of this distribution. So 1, 2, and then a half. So the score of 450 is 2.5 standard deviation units above. And again, we had indicated that this idea of noticeably different is defined by values that are beyond 2 standard deviation units. So this falls into that, what we would refer to as extreme or noticeably different. And this is giving us evidence to indicate we have support for the research hypothesis. The research hypothesis indicates that the growth hormone will have an effect on weight. And because the weight of this particular rat was significantly higher than the norm outside of that common region, then we would have support for that. Whether we reject the null hypothesis is contingent upon conducting this research on a sample. We wouldn't draw these conclusions by using one data point, but this is just the illustration of how we would convert an X value into a Z-score to, again, understand this idea of noticeably different. In inferential statistics, we're going to actually use a collection of X values, a sample, right? We would normally take a sample of, let's say, 50 rats and administer this whole growth hormone and then measure the average of the weight of those who received the treatment and compare it to the untreated population. Same process, but again, in this case, we're just working with X values. But again, this particular rat shows that it's very different in weight compared to the norm, and so we have some support for this idea that the growth hormone was effective, opposed to the other rat that only weighed 418 grams after receiving treatment. So this is the basis of inferential statistics. Again, at this point we're just using X values, but come chapter 7 we'll be using samples to draw these conclusions and these comparisons, and it'll all be grounded in this idea of probability. What is the chance that we would select a sample of untreated rats and they weighed on average 450 grams? The likelihood that a sample of untreated rats weighing 450 grams is pretty unlikely. So again, given the distribution of weights here, and we see the tail tapering off over here, that the frequency is indicating there are very few rats that weigh 450 grams. So the likelihood of selecting a sample of untreated rats weighing on average 450 grams is very improbable, very unlikely, and therefore we would have great support for this idea that the growth hormone was effective. So that's where we're moving with these ideas of a z-score indicating the distance, standardized distance from the mean, so that we can compare and determine if the independent variable, the manipulation of the independent variable, has shown some effect. And we'll end with the learning check. This is similar to the example I gave you of Mary and Esther and their statistics exam 1 scores. So you will be given these types of questions to assess your understanding of converting unlike distributions onto one common distribution, the z distribution, to make fair comparisons. So last week, Andy's had exams in chemistry and in Spanish. On the chemistry exam, the mean was 30 and the standard deviation was equal to 5. And Andy scored a 45. On his Spanish exam, the mean was 60 with a standard deviation of 6. And Andy scored a 65 on that exam. For which class should Andy expect a better grade? In other words, which exam did he perform better? And what we need to do is first recognize that these are two distinctly different distributions because of the fact that they have different averages and different standard deviations. So comparing them at face value, the score of 45 compared to a score of 65 is inappropriate. It's comparing apples to oranges. So we need to convert them into z-scores for us to make a fair comparison. So we're going to convert the first score in the chemistry test. So z is equal to x minus mu over standard deviation. So z is equal to 45 minus 30 divided by the standard deviation of 5. So we get a score of, a value of 45 minus 30, 15 over 5, and we get 3. So in comparison to his peers, he did quite well. Again, this idea of noticeably different. If we plot this out, we have the mean of the exam equal to 30, standard deviation equal to 5, and his score of 45, right, is 1, 2, 3 standard deviation units from the mean. Positive 3 standard deviation units above the mean, which is significant in showing that he did much better than the norm. He did much better than his peers in that particular class. So let's consider the other distribution and the other z-scores. So z is equal to x minus mu divided by standard deviation. Z is equal to his Spanish test score was 65, and the average was 60, and the standard deviation is equal to 6. So we have 65 minus 60 gives us 5, divide by 6. And we get a proportion 0.83. And we'll learn that, for z-scores, they're reported 2 digits right at the decimal, the 100th place. So we'll learn to use our appropriate rounding rules to cut off our z-scores. And again, this is indicating that he was pretty similar to the norm, that his Spanish exam score did not deviate significantly from the norm. So we have a norm demonstrated by a score of 60. That was the average score. And the standard deviation is equal to 6. So one standard deviation unit puts us at 66. And his score of 65 was right about here. Score of 65. So it's equivalent to a z-score of 0.83. So again, showing that it's not noticeably different, very close to the average score. So we would conclude that he would expect a better grade, or just on this particular exam, he did much better on his chemistry test because he scored 3 standard deviation units above the mean. So again, this example helps to illustrate how we take two dissimilar distributions, place them on one distribution, a z-distribution, so that we can draw fair comparisons between the two. So again, the original distribution for chemistry here and Spanish here were converted to a z-distribution, and now we were able to make fair comparison once we've converted both raw scores into z-scores. So a score of 3 was the chem score, and a score of 0.83 was for Spanish. So again, we've placed them on one common distribution, and we can see the one that's further from the mean on the positive side would denote a higher score. So again, taking apples and oranges, converting them to pairs, one common distribution, so we can make fair comparisons of two dissimilar original distributions and two x values coming from distinctly different distributions. And this this learning check reinforces the concepts that we've been presented in this chapter. So transforming an entire distribution of scores into z-scores will not change the shape of the distribution. And this is true. We've discussed it when we were converting scores in a population, and the same characteristic is applicable when we transform scores in a sample. So the shape of the distribution remains the same. Again, the z-score is simply a new label for that original x score. So the location does not change. It's now simply expressed in standard deviation units above or below the mean, opposed to raw score difference above or below the mean. The next one, true or false, if a sample of 10 scores is transformed into z-scores, there will be 5 positive z-scores and 5 negative z-scores. And this, in general, is false. It could be possible, but we wouldn't expect an even distribution of scores above and below the mean. The number of scores above and below the mean will be exactly the same in relation to the original distribution. So we may have 8 scores above the mean and 2 scores below. Again, it's dependent on what the original distribution looks like. So we should not expect an even distribution of z-scores above and below the mean of a population or sample distribution of z-scores. And that concludes the lectures for Chapter 5, and all of this information will help us better understand the concepts of probability, which will be presented in Chapter 6, and be inevitable or essential in understanding Chapter 7 when we discuss the distribution of sample means. So this is all introduction to what we're going to be exposed to in Chapter 7 when we start to really engage in inferential statistics.